speaker today is Joaquin Moraga from Princeton, and he will tell us a bunch of things about Jordan property and comatologue singularities and things.
Okay, so the title is Jordan properties for local fundamental groups. So everything I will talk about is over the complex numbers. I think that you can generalize it to algebraically closed fields of characteristic 0 without any problem, and maybe characteristic P1 needs to actually do some non-trivial work. So I think that I want to start the talk a bit like, let's say, far previously than I started working in local fundamental groups. So let me start talking about some papers that I posted on archive previously related to some local version of BAB. So I was wondering, I mean, so the current show us that if you have a Klt pair, right, with negative kx plus delta big and f, and we can sort of control the singularities of this guy away from 0. So we say that x delta is epsilon Klt, where epsilon is positive, then x belongs to a bounded family. So I will recall later maybe the definition of epsilon Klt singularities. Okay, and here x is a projective variety. So these are projective pair. Right, so maybe let me briefly recall what epsilon Klt means. So essentially, for any projective irrational morphism from a normal variety X. So during this talk, all varieties will be normal and quasi-projective, unless I say the opposite. Okay. So and then you take a prime divisor here. So this is irrational, and this is prime. And every time that we talk about pairs in birational geometry, we care about an effective divisor on X such that kx plus delta is Q Cartier. So in particular, we can pull it back. Okay, so then we define the log discrepancy of X delta to be 1 minus the coefficient at E of ky minus the pullback of kx plus delta. Okay, so this definition essentially measures the singularities of x comma delta along the tangent directions corresponding to E. So E is an exceptional divisor in some birational model, but one can understand the points of E as tangent directions on the pair, and this gives you a measurement of the singularity. So if AE of x delta is greater or equal than 0 for every E, we say that the pair is log canonical. If AE of x delta is greater or equal than epsilon for some fixed epsilon for every E, we say that x delta is epsilon log canonical. If we replace the equality by a strict equality, we will say Kawamata log terminal or epsilon Klt. And then maybe I will explain what DLT and PLT means, but maybe let me not, I guess most people here are experts on this stuff, so let me not spend a lot of time on this. So essentially, what Birkar proved in this BAB conjecture is that Fano varieties or Fano-type varieties with singularities bounded away from 0 with respect to discrepancies are bounded. So essentially, you can put all of them in a projective family. So one of the motivating questions I've been thinking for most of the time is, so is there a local version of BAB? Which I guess a lot of people have thought about this question, and there are various answers around possible conjectures, I think some people think that ACC for a minimal log discrepancies is actually the local version of DAB. So I've been playing with this question for a while to try to produce new research. And the first outcome of this was a theorem. I need to remember the year, in 2018. So by the speaker, which says the following. So the philosophy is that if you have a phenotype variety, the easier way to construct a Klt singularity is take the cone over it. So you take the cone over the variety with respect to your favorite polarization, and this one will be Klt. So the first question that I ask myself is, well, is there any boundedness theorem for cone singularities? So you start thinking locally, but at the same time you think about the local version, which is closer to the projective version. So these are cones. If you go away from the world of cones, then everything gets more complicated. So the theorem is like this. So fix D and epsilon. So D and N are natural numbers and epsilon is a positive real number. So the set of D-dimensional cone singularities with isotropies which are epsilon log canonical and have isotropies bounded by N is bounded. Okay, so let me explain you the statement. So here we're talking about boundedness of singularity. So essentially, well, I guess the definition of boundedness you can use the same. Here you don't have a polarization, but essentially it means that there is a variety of finite type. So there is some big space of finite type, right? Such that for any singularity, as in the statement, so for any singularity x in X, and this is a statement, you're going to find a point here, 0, such that if you localize and take the completion, it becomes isomorphic to the corresponding completion of the localization. So it's a very local statement, I would say, formal. So what do you mean with isotropies here? Well, the isotropies is just the well, you just look at the stabilizer of each point. So the stabilizers are either the stabilizers for these actions is, well, with cone singularity here we mean that we have a GM action on the singularity, a GM action with a vertex. So there is a unique fixed point lying in all orbit closures. Okay, and then that's actually the definition of the vertex. And then the isotropies are the order of the stabilizers. For instance, well, the stabilizers will be GM itself or some finite subgroup generated by a root of unity, right? So essentially, we're bounding the length of this root of unity. So the idea is pretty simple of the proof of this of this term. So the idea is that you prove that using the bound on the
sorry, a question.
Yes.
If you consider a singularity like this, so you are considering this with embedding, right? Because
yes, with some affine embedding.
So you fix embedding because you see once you have GM action is equivalent to choice of embedding, right?
Right.
I see. Okay.
Yeah, I mean, you can actually think that that this action, the cone action, gives you some give you naturally like a polarized, anti-canonically polarized phenotype variety, because you take the Chow quotient. So the,
Yes,
I mean,
yes,
the idea of the proof is actually that the idea of the proof is to use some adjunction and Chow quotients to actually prove that if you have a singularity like this, you can quotient by this GM, and then you get a projective phenotype variety such that X can be reconstructed as a cone on Y with respect to some ample Q divisor. So the first step is to prove that Y is bounded. And essentially, some not so hard computation shows that for some boundary, negative ky plus delta y is epsilon over n log canonical nef and b plus nef plus b. So here one applies BAB straight, and one gets that A is bounded. And then some further game actually proved that A is linearly equivalent to a divisor, so such that Y comma D is bounded, is log bounded. But if you change linear equivalence in a projective variety, the corresponding cone doesn't change. So that gives you that since the pairs Y comma delta Y comma D are log bounded, this actually gives you the fact that the cones are bounded. So if you think about it, well, the proof is not hard. It uses like really straight techniques from the field, but for me, it's a nice local version of BAB. So then I try to understand a bit better. Well, of course, this is the naive case, right? When you work with cone singularities, as I said before, this is the affine case which looks closer to the projective case. So what can we say in general? So that brings us to the definition of Plt blocks. So let me explain you what Plt singularities are. So essentially, a Plt pair is a log canonical pair. Plt pair X comma D is a log canonical pair which has a unique E in X with AE X comma D equals 0. Okay, so log canonical means that this log discrepancy is greater or equal to 0, and here we have a unique E that hits this value. Well, okay, so some people will complain about this, which possibly, so I should add the word possibly here. Okay, because people say if you're Klt, then you're Plt. But when I say Plt, I usually mean that there is a divisor with coefficient 1. So essentially, what this means is that you have your space X, and inside the boundary, you have a divisor with coefficient 1, and then everything else outside that divisor of coefficient 1 is Klt. So in particular, if you do adjunction inside here, you get something Klt. Okay, so theorem of Cheng-Yang-Xu says that if you I don't remember the year, but it says that if you have a Klt pair, so X in X comma delta. Okay, I'm having some small technical issue. As expected, I cannot write anymore. So. Okay. Can you hear me?
Yes.
Okay, this will just take 1 minute. I think sometimes the points I was teaching before, and sometimes when I write too much, the tablet needs like a second to. Okay, I just reopened the. Oh no, it's still frozen. Okay. This may take 1 second, sorry for this. No, well, I didn't expect this, but I'm having technical issues. For some reason, when I put it in tablet mode, it freezes. But this has happened before, so usually it takes a minute or two to come back. So it somehow detects my finger, but it doesn't detect the pencil. Rotate or something. Okay, let me try some other thing. So I will try to open the some other app different than this one. So can you make me a host of the Zoom to share something? Okay, I think I should already be host, right? Okay, let's try to use the Zoom. Okay, this seems that it's working. Okay. Okay, so it seems like I can write here, but for some reason it's not detecting. Okay, now it's working. Okay. Okay, we have to change the app. Okay, now it's working fine. Actually, maybe this one will work now too. Okay, perfect. So it was just, as I say, like sometimes it gets overwhelmed with too much writing and it needs some time. Okay, now we're back. Okay, so the theorem of change and choose says that if you have a Klt singularity.
But at the moment, we don't see your screen, I think.
Okay, that's a good point. Share screen and a screen. Great. Yeah, sorry for that. I was teaching before, and sometimes when I'm writing for too long in the tablet, it freezes like after 2 hours. Okay, so now we're back.
Now I think everything is great. Yeah.
Okay, so there exists a projective birational morphism that extracts a unique divisor E mapping to X such that Y delta Y plus E is Plt and negative E is ample over X. So essentially, this term of Xinjiang says that you can do some special block that will extract. Well, after doing a junction, you will see that E is actually a phenotype. So you extract a unique phenotype variety over your singularity. And this is really useful to study the singularity itself, because you can reduce local problem to global problem. But in general, like, not every problem can be reduced to the global setting by doing this. So essentially, there are usually two extremes of to tackle problems. One is try to reduce a local problem on X to E, and this is like something that one can try. It doesn't work in possible programs. The other one is use the generation theories, or the generation theory. So essentially, one tries to degenerate the singularity to the cone over. So you just do the generation to the normal cone of Y. So you have the cone of E of Y of E restricted to E, and this that's what we call X naught. And you can actually see that your singularity X degenerates to the singularity X naught. And sometimes you can use some geometry here and try to extend results to the starting Plt singularity. But in general, we know that both in general, these two approaches are difficult, because not every problem can be lifted to the exceptional. And also, we know that when you do a flat deformation of singularity, you will probably lose all invariants, right? If you have any invariant in algebraic geometry, they tend to be upper semi-continuous or lower semi-continuous. So controlling it on the central fiber not necessarily would imply nice control on other fibers.
Sorry, and the theorem claims that such a blow-up exists, right?
Yes. Yes, sorry. There exists. And of course, this is not unique. For instance, if you have a toric singularity, all toric blow-ups are PLT. So it's highly non-unique. But at least it gives you the existence of such objects. So this brings me to a second approach to try to understand what a possible local VAV could be. So this, again, a theorem, I think, 2018, which is the following. So fix epsilon positive and delta positive. Okay, sorry, before stating the theorem, I will do a refinement of the definition of Plt blow-up. So this object that we have here is what people call a Plt blow-up of the singularity.
One remark. Excuse me.
Yes.
This notion was introduced actually proved in my old paper much earlier than Q.
Yeah, I actually. But did you just prove it for trifos or?
Yeah, model MMP, of course.
Okay.
In that time, it wasn't general MMP wasn't known, so it's like this. Okay.
Yes, you're right. Sorry, I forgot to mention this. Professor Prokhorov actually proved this modular MMP back in the 90s, maybe.
Yeah, it's a very old one.
Yeah. Sorry, sometimes forget about something in the literature. So we define a delta Plt blow-up to be a Plt blow-up so that Fe is delta log canonical. So essentially, a delta Plt blow-up is a special sort of blow-up in which you control the singularities of E away from zero. So you can say that this definition is a bit made up to apply VAV to the context. So a second theorem that one can prove is the following. So if you control the log discrepancy of the pair away from zero, and you control some blow-up, then you can control the minimum log discrepancy. So the singularities X in XD, which are epsilon log canonical and admit a delta Plt blow-up have finally many minimal log discrepancies. So essentially, what I'm saying is that we have this invariant called the log discrepancy. If you can control it in the singularity, so this is epsilon log canonical, and furthermore, you can do some extraction and control this invariant in the exception. So this is delta log canonical, and epsilon is away from 0, and delta is away from 0. Then you can only take finally many values of minimal log discrepancy. So for instance, a counterexample, like a non-example of these terms are AN singularities. Well, those have minimal log discrepancy 1, but the point here is that, for instance, they don't admit delta Plt blocks. If you do any Plt block of a AN singularity where n increases, all possible Plt blocks will have log discrepancy at most 1/n. So all possible Plt blocks will be at most 1/n Plt. Okay, so later on with yeah.
Excuse me, again, in your definition, above definition for delta log canonical, is it for E itself or E its boundary?
Sorry, actually, it is for the boundary one. So it must be for the one that you obtained by adjunct.
So you say that E is delta LC. It means that E itself or E with a boundary.
With the boundaries, right? Maybe.
Yeah, because in your example, it's just curve.
It's just P1. Yeah. Sorry, I missed the boundary here. This is the boundary obtained by adjunct. Because right, otherwise here all the extractions extract P1. But if you take the boundary, the orbifold extractor for dimension 1 point, then you will obtain points with the form 1 minus 1/n. So the log discrepancies goes to 0.
Is it related to exceptionality of singularity, existence of such a blow-up?
Right. So actually, this term says that a corollary of this term is that n-dimensional exceptional singularities only have MLDs accumulating to 0.
Okay. I
so
see.
Essentially, one corollary of this theorem is ACC for exceptional MLDs with the standard boundary. So a standard boundary means of the form 1 minus 1/n, where n is some positive integer. And actually, when I posted this paper on Archive, I got an email from Shokuro, in which he told me that he himself with Han, one of his postdocs, and Liu, which is a student in Utah, they prove ACC for exceptional MLDs in the general case. So for, let's say, for parents, X delta, but they don't put any assumption on delta. Actually, it can be an R divisor. So the idea is always the same. The idea is trying to apply a theorem of the following form. You do a Plt block, you control the singularities along the Plt block, and essentially that allows you to control the minimal log discrepancy. Because now E is bounded, and then you can essentially reduce all the computations to a bounded divisor. And then, in further conversations with these two guys, Han and Liu, we realized something quite nicer. So you have this notion of epsilon log canonical singularities and you have this notion of delta Plt blocks. So the natural question is, what can you control if you control both? And we started looking at some invariants, and we realized that essentially every invariant that you could look at is controlled by epsilon d. So if epsilon is bounded away from 0 and delta is bounded away from 0, then you control all invariants of singularities. And then working a bit harder and using the boundedness theorem that I wrote before about cone singularities. So using this theorem, one can prove the following. Theorem, and this is work together with Han, the author and Liu, and I think this was maybe 19 or 18, is that so you fix epsilon away from 0 and delta away from 0, then the set of epsilon log canonical singularities with which admit delta Plt block are bounded up to the formation. So what do I mean with bounded up to the formation? This means essentially that all of them are deformations of a bounded set of singularities. Well, it's actually a bounded set of cone singularities. And here the proof is not very hard. So let me tell you what is the idea. You take your epsilon log canonical singularity, and then you take this delta Plt block. By VAB, you know that the E here is bounded. And then you do the generation to the cone. So essentially the generation to the cone is isotrivial in the blow-up, but then contracts down to a cone singularity. And then using some computations, one can prove that this singularity that appears on the central fiber is epsilon over delta log canonical. So okay, maybe here I'm writing something wrong, but let me just write a function on epsilon and delta log canonical, and isotropies are bounded by a function that only depends on delta. So maybe it was 1 over delta. So now we are in the context of cone singularities with bounded log discrepancies and bounded isotropies. So this with bounded, it means bounded above. And these, all the other bounds I'm putting here are below. So by the boundedness of cone singularities, this is bounded. But then we are exhibiting all these singularities that are epsilon log canonical and delta admits a delta Plt block as deformations of a bounded family. So essentially, every invariant that is lower semi-continuous will be controlled for these singularities. Well, you can ask the questions is, are these singularities bounded? I mean, here we're just showing that they're bounded up to the formation.
Of course, analytic deformation, right?
Yes, this is an analytic deformation.
You mean?
Actually, this this deformation is isotrivial outside the central fiber. But it is an analytic deformation. If you want to work over, I don't know, not over the complex numbers, you can do the same over the centralization or something. So then you can ask the questions, are these singularities themselves bounded? And the answer is no, and there is a counterexample here. So you can consider the family. So example, you can consider the family xn is equal to x squared plus y squared plus c squared plus c squared w plus t w to the n equals 0. This is inside A5. and has a morphism to A1T. And essentially the point is that, well, X and 0 is isomorphic to a fixed X0 for all n. Okay, and then you can do a PLT direct system. Well, you have this deformation to the central fiber here, X0, and you can do some sort of PLT blow up in the whole family. So essentially, you blow up the line X equals 0, Y equals 0, Z equals 0. And one can see that all these singularities, all the general fibers, X and T, where T, I think you need to take it general, not even very general. So admit PLT blow up, a delta PLT blow up with this delta is some fixed number that doesn't depend on n, and well, all of them are epsilon log canonical for some epsilon that doesn't depend on n as well. And okay, so why this? So essentially, so far I just exhibited you an example, which are epsilon log canonical and delta PLT, and then the claim is that these singularities are not analytically equivalent. But to do that, one just compute the Turina number of X and T, which is just the dimension of the space K X, Y, C, W divided by the ideal of the singularity times with the Jacobian, and one see that this number is actually n plus 2. So since the Turina number can tell apart analytic singularities, these singularities that appears in this family are actually not analytically equivalent. So this also gives an example that there is no lower semi-continuous invariant that can bound Klt singularities. So there is no, I mean, if you want to bound singularities, you have to put really restricted conditions, because then you will need to somehow control the deformation space of a Klt singularity. And if you erase this part, right, if you just have X naught, this singularity X naught is a Klt singularity with infinite dimensional versal deformation space. Right, and what I'm saying is that in this versal space, you can go to accountably many directions such that the singularity stays Klt. Here one has to be careful, right? Because if you deform a Klt singularity, Kx plus delta or simply Kx may not be Krt anymore. So not every possible direction in the versal deformation space will give you a Klt singularity. But if you choose your deformation somehow cleverly, then most of them will be Klt singularities. So I mean, this is a simple example that shows that there is no way to bound Klt singularities fixing a single invariant. But the best that you can do is to talk about boundedness up to deformation. So it seems for me that at least this direction of the direction of bounding epsilon and delta seems difficult to apply in general pictures, right? Because, well, epsilon is not hard to bound when you have a sequence of singularity, but controlling this PLT blow up, it seems like really hard in applications. There are some examples in which this can be done, and there is some work in progress to apply this to some situations of singularities, but in general, this is difficult. So, but something that one learns from this is the following. So let me explain like this. So when one tackles ACC for MLDs, essentially there are two possible things that people have been doing in the past. One thing is fix the singularity and move the boundary. Right, so there is a lot of work on this direction by I think Kawakita, Mircha, Nakamura. There's more people that are forgetting. So essentially, you try to understand the minimal of discrepancy of a singularity by fixing the year and moving the boundary, and this is already a hard problem. But then there is other one that is like try to look at a special sort of singularities and prove the ACC there. So So if you think about it, this ACC for exceptional singularities falls in this second category. We take a special sort of singularity that has a nice property, and then we try to prove ACC. So if you think about this special sort of singularities, then there are a lot of work done, right? There is like the surface case, was done by Shokuro, Alexiev, and probably there's more people there. And then there's the toric case, I think mostly doing by Ambro. We have the exceptional case now, and we have some threefold cases. Not all the threefold singularities we know that satisfy ACC for MLDs, but at least we have some cases. So, but all these singularities have something in common. So in all these singularities, we can control the local pi1. And it seems that if one look at the proofs of all the cases of ACC for MLDs that we have in special classes of singularities, of Klt singularities, the main root, or one of the main properties, is that we can control the local pi1, and we understand if you have any divisor for the singularity, any effective divisor to the singularity, you know where it lies in the, where the corresponding cyclical lies in the local fundamental. Okay, so then this motivates me to understand better minimal discrepancies of the singularities. One actually needs to understand better the local fundamental. So what we know about the local fundamental group? There is a theorem by Chen Yang Chu that says that the local fundamental group of Klt singularities is finite. And then, if one looks at the examples before, the exceptional case, the toric case, and the surface case, and even many of the threefold case, one fastly realizes that essentially most of this finite group is abelian. So this motivates me to look at the following picture. So let's take a singularity here, x in x, and let's take its universal cover. So when with local fundamental group, I always mean is essentially the pi1 of a really small analytic ball around the point intersected with x minus the point. And well, since this is a CW complex, one can prove that this, for epsilon small enough, these groups stabilize. So this is just the quotient by G, which is a finite group. So now let's do a Plt block here. So we extract E. And now let's take the pullback of this diagram, the fiber product of this diagram, then normalize it. And then, well, here you have a G action, and then the G action lives here. And here you have some divisor E prime that's a G is a cover of E. So this is phenotype, and this is also phenotype. But now, of course, G is not acting on E, but a quotient of G. A quotient of G is acting on E prime, which is of phenotype. And this is a finite group. This quotient of G is finite. So by the Jordan property of automorphism groups proved by Prokhorov and Framov, one knows that this quotient of G is mostly abelian. So let me just recall what is the result. So we say that a family of groups satisfies the Jordan property with respect to K, if any finite subgroup of a group in the family contains a normal abelian subgroup of index at most K. And this is called the Jordan property because Jordan proved this for GLN. So if you have a finite group G, a finite group of GLN C, then you can find an abelian group A inside G of rank at most N and index at most Cn, where Cn is a constant only depending on N. Well, actually, I think that in the papers, I don't know if they stated. So let me just state the theorem of Prokhorov and Shramov as this. I don't remember the year, or maybe you remember. So actually, they talk about birational automorphisms and rationally connected varieties. But for this context, let's just stick to more suitable version. So the automorphism group of phenotype varieties of a fixed dimension satisfies the Jordan property and furthermore, I don't know if they actually write this down, but it just follows from their paper. Furthermore, the rank of the abelian group is bounded by the dimension of the varieties. Okay, so how we go from here?
Can I ask a question?
Yeah.
So at the moment, this is not applicable to your whole finite group. It's applicable only to its quotient, right? Because you don't know if the action on the divisor is faithful.
Yeah, you know, but I haven't given a proof of the Jordan property of the pi one yet.
Yeah.
Right?
Sorry?
So I haven't given a proof of the Jordan property of the local pi one yet. I was just this is just a motivation of why I think it could work. So it's true. We have the Jordan property for the quotient of G so far. So now I will tell you how to go to G. Okay.
Yeah, great.
Okay. So the point is the following. So now let's see. Well, let's state the theorem. This is a work that I did back in Utah with Filippazzi and Roberto Sbaldi. Well, I actually think that well, it should appear on a page soon. I actually think that we did most of this on MSRI. So the local fundamental group, the local fundamental group of Klt of n-dimensional Klt singularities satisfies the Jordan property. And the abelian group
sorry, I missed. Do you consider usual fundamental group or algebraic fundamental group here?
You can consider both.
Just usual, I think, right?
You can consider the usual or the profinite completion. So let me tell you what the idea of the sketch of the proof is, and then I will tell you why you can also consider the usual one. So probably you're thinking about this conjecture of Collar that the local fundamental group is finite. Because okay, so what? Okay, maybe I have to do some. Yeah, I have to do some fixing here. So here, I should write the profinite completion. So maybe this is what Prokhorov is complaining about. The complaint, what Cheng-Yang proved is the profinite completion of the local fundamental group is finite. But actually, I should comment this here. Lucas Brown, there is a postdoc of Quebecus, actually proved the conjecture 2 weeks ago, and is posted on archive already. So the local fundamental group. And the proof is a really beautiful proof using Chaparevic maps and automorphic forms. The local fundamental group of a Klt singularity is finite. Okay, so actually now we have the two versions of the theorem. We have the one of the local fundamental group, of course, the profinite completion. If you know the local fundamental group is finite, then the profinite completion is finite. Okay, so let me draw you a sketch of the proof of this one. So as Professor Samo said, I mean, my motivation sketch only works for the quotient, for a one-dimensional quotient of G. So essentially, what is the goal is try to lift this abelian group from the quotient to G itself. So how we do that? So essentially, we start with this Plt block, and something that one can see that essentially comes from the theorem of Blocker-Van-Flammer is that actually the pi1 of E delta E restricted to the smooth loci is satisfies the Jordan property. Essentially, you just take the universal cover and apply the automorphism group statement on the universal cover to satisfy the Jordan property. So essentially, the first point is try to translate everything into fundamental groups. So now you have the map pi to x in x. And what you do is you take a small analytic neighborhood around x. So let me call it U. And then you look at the corresponding inverse image here. So since we care about the local fundamental group, right, we're deleting x. So actually U doesn't see this blow up. And something that we know from linear stratification theory is that there is an exact sequence. So there is an exact sequence between some cyclic group, the local fundamental group of the singularity, and the pi1 of this one, of the log smooth loci of the phenotype variety that we extracted. But the point is that we know that this satisfies the Jordan property. So here there is a normal abelian subgroup of the right rank and the right index, so bounded index. So, but then of course, if I call this f, and then if I call this f and take f inverse of AE, well, there is two problems, right? Problem one is this guy, and problem two is that if you take two elements A, B here, maybe their preimages may not commute. And of course, these may not commute. So here there is like a really, well, it's topologically easy to prove. I mean, so what we do is the following. So let's say that this is a singular locus. So this is the singular locus of P. So what we do is we take an analytic neighbors of the singular locus. So you essentially like fathom a little bit the singular loci, and we know, sorry. So we made the singular loci a bit more fat, and we will call this E delta SM. So essentially this is E minus some analytic neighborhood of radius delta of the singular loci. So it's easy to see that the pi1 of E smooth delta E, so this is just some orbifold structure. So this actually surjects into pi1 of E SM delta E. Okay, so now the trick is the following. One can prove that after making the singular loci like a bit thicker, this vibration, I mean this long exact sequence of homotopies splits, because then if you pick the stratification correctly, you can actually prove that the normal bundle is trivial on this thickening of the singular loci. So essentially, you lift every computation from this exact sequence to this pi1 of ESM delta. But now we know that the sequence actually splits because it's a trivial bundle on this guy. So here we have C, here it rejects, here I'm not claiming it's injective, and then here you have just pi1 of E smooth delta. Okay, we have this. Okay, and all inclusions, all morphisms, sorry, all homomorphisms come from inclusions in topology. But now we know something, we get some extra information from this. From the 4 lemma, sorry, I think this should be Z. So we know that this is surjective and we have a morphism here, and we know that this is surjective. From the 4th lemma, we conclude that the middle one is surjective as well. And then the upshot, I won't do all the details, but the upshot is to take the nice abelian group that we generated here with Prokhorov-Shramov. So this is generated by A1, AN. You leave the elements here. Then you just take the inverse image here, which, I mean, using this trivial topological fibration, and then you push them here. And by doing so, one can actually prove that their pullbacks commute here. I mean, not pullbacks, but you can choose. So we can choose for images that commute. And something that comes for free on this diagram is that the image of C, the image of CM inside the pi1 lies in the commutator. Because it actually lies in the commutator here. So this helps us to overcome the 2 main difficulties of lifting the normal subgroup from the exceptional to the local pi1. And then, well, maybe I don't want to write down all the details of how we do this, but it's just some group theory. So the only important thing is doing this Plt Block, applying Prokhorov-Shramov on E, and then lifting using some triviality of the fibration in some open analytic set of E. And then the rest is just some group theory. So this is the idea of the proof. So let me tell you some other directions. So actually, with Lucas Brown, we're generalizing this to the smooth loci. So the arguments should be really similar, but we prove the Jordan property for pi1 X smooth around X for Klt singularities, for n-dimensional Klt singularities. So you see here in the paper with there's a draft now, probably will be posted next week. With Stefan and Roberto, we only talk about the local fundamental group. So essentially, you just delete the central point and then you look at the open set, the small open set around. But actually, with Lucas, we're proving that you can do this same game, but if you delete the whole singular loci and then you restrict to a small neighborhood. And this is way more beneficial because we know that the class group of the singularity, the local class group, if you want, embeds here. So this tells you the following. Every time that you have QRT divisors of high index, then it will imply that you have a large abelian subgroup here inside the local. I think Lucas likes to call this the regional fundamental group, not the local. I don't like this notation, but well. Also, he usually likes to write X reg. Let me tell you some applications of this Jordan property. So the first application is the following. So some applications. So the first application is the following. So some people has been interested on iteration of Cox. So essentially, if you have a phenotype variety, right, and you apply the Cox, then you get a Klt singularity. And this is known by the work of a lot of people, probably Morgan Brown, Gongyu, and some other people, right? And this is beneficial for many reasons, right? It's better to study the Cox because then you represent your projective variety as quotient of some nicer object usually. And there's more reasons that sometimes you have you want to study Q points on X, but this translates to studying integral points on the Cox ring, right? So sometimes it's way easier to find rational points by looking at integral points in the Cox ring, right? So why just do it once? Well, you know that the Klt singularity is also a Mori dream space over itself, or well, even you can say a Mori dream space itself. Okay, so you can also take the Cox ring of the Klt singularity, and this is what usually we denote as Cox2 of X, which will be just another affine singularity. So this is the quotient by some torus. And when I say torus, I don't mean actually a torus, I mean a quasi-torus. And then you can apply the Cox again, and now you have Cox twice of X, and this is the quotient by another torus. And this is not, probably this morphism is not abelian, but it's split as two abelian morphisms. So we will say that this is a semi-simple morphism because it splits as two abelian morphisms. Okay, and you can keep doing this. So the first question is, does this process terminate? So Lucas proved Brown gave a positive answer in some cases. So I think that he worked with cone singularities and weakly phenotype varieties. I don't remember what he means with weakly phenotype, but I just remember the word in his paper. So something that we can prove now is the following. So take X, a phenotype variety of dimension n, and take the iteration of the Cox ring. So this is interesting. Iterating the Cox ring is interesting. Well, let me give you another reason. Well, it's similar to the reason I gave previously. So if you want to look at rational points here, it's the same as looking at integral points here. But then when you look at integral points in the second iteration, the arithmetic degree, the arithmetic phi of these points will start increasing. So if you keep iterating this process, philosophically, I'm not an expert on this part of algebraic geometry, but philosophically, finding points on the iteration should be easier than finding points on the first Cox ring. Okay, I don't know how precise a statement I could prove about that philosophy. So this stabilizes. And the interesting thing is that it stabilizes for Cn, for k greater or equal than Cn, where n only depends on the dimension. So if you iterate the Cox ring of phenotype varieties, they all stabilize at the same point. I mean, not the same point, but there is a point that only depends on the dimension, such as you cannot keep taking the Cox ring, where n only depends on the dimension. So you can also apply the same process for Klt singularity. You can start with the Klt singularity and take the Cox ring of the Klt singularity and start iterating the construction.
So this is C of n that depends on dimension, right?
C of n, yes.
N is dimension itself.
Well, the statement was right, but the theorem, yeah, Cn only depends on the dimension. Okay, so if you start iterating the Cox ring, you will obtain. So philosophically, is a nicer Klt singularity, and this is nicer than the previous iteration. So let me try to explain you what the actual theorem is, what the actual corollary is of this iteration. So there exists for any Klt singularity. Okay, so let me say a word before this. So now you can ask the following question. So the Cox ring measures abelian covers. It measures abelian covers that may be non-finite, right? And on the other hand, you can measure finite covers. So the finite covers are measured by the pi1, and the abelian covers that may be non-finite are measured by the Cox ring. So the natural question is, how much can you improve a Klt singularity by doing these two sort of coverings? So how much can you improve? And that's this process terminates. If you start taking abelian covers, finite covers, abelian covers, finite covers, will it terminate? And well, furthermore, you can ask if it terminates in a unique object, how much the singularity improves. So we give the following answer to all these questions. So for any Klt singularity, x in x, there exists a unique up to isomorphism. Let me remember, this has a lot of words. Factorial, canonical, simply connected, or locally simply connected. So here it means that the local fundamental group is trivial. So this means by one of y smooth or y at y is trivial. Singularity y, so that we have a quotient from y to x, quotient by g. Of course, they may not have the same dimension, right? Because once you take the constraint y, once you may go up in the dimension. But the interesting part is that g is a torus of certain dimension k. Now I mean here a torus, a legal torus, just gm to the k. Similar product with by one of x smooth. And furthermore, k is bounded by the second homotopy group of x. So this seemingly scary inequality, it just comes from some long exact sequence of homotopy. And is unique. So here I should make a remark. This is unique if t is k is minimal. Of course, you can just multiply this singularity by t and then keep going higher and higher. But of course, that will don't change the factoriality, the canonical singularity, nor the locally simply connected. So if you pick k minimum, it is unique. So it's sort of one improvement of the universal cover of the singularity. So this is like a universal cover that is also factorial. And in many cases, it seems that it's useful to compute invariance. So you go to this really nice singularity answers, and then computing some invariant answers seems nice, seems easier, and then you can try to understand how your invariant behaves when you quotient by G. Okay, so let me tell you a bit more motivation about the Jordan property. So what is another reason why I started thinking about the Jordan property? By the way, let me just mention that this term that I wrote here, which one? Okay, so this one should work in full generality. So this what do I mean with full generality? Is that it also works if you take boundaries and also works in the relative setting. So essentially, we prove that if you have any morphism of phenotype, you take any point in the base and you take a small neighborhood of the fiber and you subtract the fiber, then the pi1 is finite and satisfies the Jordan property. Which at the end of the day, everything boils down to program Shramov and then using some topological trick like this to lift the abelian group that program Shramov already constructed. And it's never too hard because in all these cases the quotient of G will act on the phenotype variety. So the lifting you're just lifting by one element. So it cannot be so hard. Okay. So let me tell you another reason why I started looking at this Jordan property for GLN. So we want to understand quotient singularities better. For instance, when I was talking about ACC for MLDs, I think, or as far as I know, we don't have ACC for these singularities. But let me tell you how the Jordan property may help to prove ACC in some cases for quotient singularities. So you start with Cn and you start with a finite action on Cn. Okay, so a subgroup of GLN. And then you apply the Jordan property and you know that there is a big, so this is index bounded by Cn. Okay, so you can also assume that the action is unramified in the codimension 1. This is just Chevalier-Shepard-Todd theorem, right? If it ramifies the quotient, if it ramifies in codimension 1, the quotient is already also Cn, so you do nothing and you start from there. So you quotient by A, and now T is toric. And then you quotient by what is left, let's call it N, by non-abelian, and then you obtain your singularity X. Okay, so the question is how we understand the MLD of X. So even if this finite map has degree bounded by Cn, it's not clear how to compare the MLD of T with the MLD of X, right? Because it may happen that you have the, okay, so let's see that this is the real numbers going here. So, and this is the MLD, this is the evaluation computing the MLD of T. And this is some other evaluation with log discrepancy at F of T, okay? It may happen that this action keeps this MLD, but quotient this by Cn or something like this, and maybe it will pull it down. So controlling just the MLD of T doesn't control the MLD of the quotient, even if the quotient has bounded degree. So, but there is a nice trick to prove some version of ACC for MLDs for quotient singularities using the Jordan property. So now let's imagine that the MLD of X in X belong to the set 0, comma, 1 over Cn. So now we only want to prove ACC for MLDs on a small neighborhood of 0. So let's here have the extraction of such valuation. If you do the fiber product of the diagram, here you have the extraction of the corresponding valuation. Let me just call it E, not T prime. The corresponding valuation on T, and this is just T. Oh, no, this is T prime. Okay, but you see that the log discrepancy at ET of T is at most 1. Okay, so let me actually write a open here. So let's say that it's less than 1. Okay, but this means that ET is extracted by a toric morphism. And now, the only case in which the MLD can change is when some subgroup of N, some subgroup of N fixes E point-wise. Point-wise. Okay, but then there is a easy lemma that shows that if you have a toric automorphism, toric affine finite automorphism. So actually, we're assuming that this automorphism is inside GLN, or it descends from GLN, which fixes point-wise an exceptional toric divisor then the action is by roots of unity on the torus. So what I'm saying if there is any subgroup of N that is changing the minimal of discrepancy, actually is inside the torus. So you can take that subgroup, let's say n prime, and move it to A. I mean, if you quotient by n prime, then you remain toric. And then a simple argument on well, induction on the size of n tell us that on this interval, the MLD of x in x is equal to the MLD of t in t. So around 0, all quotient singularities are toric singularities. Sorry, around 0, all quotient MLDs are toric MLDs. So these are, I think, a nice motivation of why we care about the Jordan property, because even in the simple case of singularity, it already helps to complete the minimum of discrepancy. So there is some hope that in the future, when we understand this picture better, how the A part acts on the singularity, we will get how to compute minimum of discrepancies better. So essentially the philosophy, and I think probably, I don't know if this philosophy is mine, probably I heard it from Shokuro, but then I believe it, is that A is actually the part that changes the MLD. The abelian part is actually the part that changes the MLD. And N shouldn't change the MLD. Well, there are examples in which N changes it, but it should not change it. It should sort of change it in a really bounded way. Okay, so this is just a philosophy. It's not a theorem yet. Okay, so then the main question becomes the following. So everything becomes the following. At least for me, which this is what I'm trying to understand right now. So now we have the Jordan property. So what happens if A is large? So why I mean with A large? So you have your singularity or your phenotype variety or any phenotype morphism, right? And we know that there is an exact sequence, A by 1 of x smooth. Well, here you can work on the singularity or over some base, and you can put some boundary if you want, and here you have the non-abelian part. So we know that this is bounded by the dimension. And we know that this has rank at most n, but it can be unbounded. So it can perfectly be A could be isomorphic to Zm to the K, where K ranges between, well, we actually want it to be large, so K will range between 1 and n, and M, let's say that is large compared with n. So it's larger than some constant only depending on the dimension. So then the question becomes, does A reflect on the geometry of the, well, here you can write a lot of words. Phenotype variety, if you set C equal to be a point, if you set C equal to be the X smooth itself, then you should write Klt Singularity or phenotype morphism, etc. Of course, among these questions, the easier one is the phenotype variety, because we have finite action and a projective variety. It's easier to deal with than a finite action on a fine variety. Those are usually more scary. So that brings us to the last term that I want to mention, and afterwards I will just talk about conjectures. So I can tell you the answer of this question. So in one case, so I can tell you what happens if A is large and you're acting on a phenotype surface. So let me give you the case of full rank first. So well, the statement starts like this. There exists a constant K, or let's call it M, or big M. Well, here maybe I'm being a bit naive, right? I'm writing A as zk to the M. You could argue that actually one should write something like this, right? With all the MK, with all the MIs being large enough, but for simplicity, let's just stick to Zm to the K. It already makes the picture interesting, and going to the general case is not far from there. So there exists a constant M satisfying the following. let X be a phenotype surface with A equals GM square inside the automorphism group of X with M larger than this constant M. Then X contains an open set, contains an A equivariant or A invariant open set, isomorphic to GM square, so that A acts by roots of unity on GM, on GM square. Furthermore, so let's call this open set U. Okay, furthermore, there exists delta contained in X minus U reduced so that X delta is log canonical and Kx plus delta is linearly equivalent to 0. So this is what people call a one complement. So essentially it is one complemented, and if you throw away the one complement and maybe something more, you get a torus. And the action of A in the torus is well, just by roots of unity.
So you don't say that this surface is toric, right?
No, it's not toric. Yeah, I think I sent you my first conjecture that it was toric, but it was false.
I see.
So let's say that it's a nice compactification of the torus, but it's not toric itself. So actually, the counterexample to this was given by me by Professor Ramos. So let me give you an example in which is non-toric, but it still contains a torus. So you consider xn to be x to the 2m plus y to the 2m plus zw equals 0 in the weighted projective space 1, 1, and n, right? So let's draw. Well, of course, we have a lot of nice automorphisms here, right? You can multiply by the 2n root of unity on x. You can also multiply by the 2n root of unity on y. But actually, these are the same because of these weights. So let's forget about one of them. We can swap x with y, and we can swap z with w. And also, we can multiply by tt inverse on zw. So again, the claim is not historic, but it contains a torus, and the compactification is somehow nice. So the compactification is in such a way that you have a one complement in the complement of the torus. Okay, so you see here you have a zn square inside out of xn. So this is Fano. Well, it's phenotype. The Picard rank I think is pretty large. And the singularities are actually converging to the canonical when you increase n. So let's see. So this is just generated by, well, you can take the root of unity on the torus and you can take mu. So this is generated by mu, and let's say mu t is the root of or maybe let's write the 2 here, the 2n root of unity inside the torus. So let's draw the surface. So the surface looks something like this. Xn, here you have x equals 0 and y equals 0. So this x equals 0, y equals 0. Here you have the point 0, 0, 1, 0. So this is w equals 0. And w equals 0 is 2n lines. And then z equals 0 is also 2n lines. Okay, so a simple computation shows that kxn plus x equals 0 with reduced structure plus y equals 0 is linearly equivalent to 0. And xn, x equals 0 plus y equals 0 is log canonical. So this is the one complement that the theorem predicts. Now, let's look at what happens when you blow up these points. So you blow up and you obtain a surface that looks like this. So these 2 points are toroidal. The points of intersection of x equals 0 and y equals 0 are toroidal because they have, well, this is q factorial and they have 2 lines with coefficient 1 to them. So they are toroidal. So you obtain something like this. If you pull back this divisor that I wrote over here, the coefficient that you obtain is 1, 1, 1, 1. And the two end lines will become separated. Right, so now you have two end lines here and two end lines here. So let me be more careful with my two end lines. Okay, but actually it's a equivariant morphism. So if you are like well, actually in this case I think this is an a equivariant minimal resolution. And then you can write you can run an a MMP, an equivariant MMP that will contract these two end lines. And then what you get is a smooth surface with Picard rank 2 with a modifiable space to be 1, and it has 4 lines with coefficient 1. So which surface is this? It's just P1 times P1. Or maybe actually it will be a Klt group, right? But well, in this case, actually what you get is a P1 times P1. So the reason why you get a P1 times P1 is because of these two extra automorphisms. That's to be. This automorphism or this automorphism essentially tells you those automorphisms are the ones that move these two, that swap these two lines, and the one that swap these two lines. They survive when you do this inverse AMMP and then you go to the singular model. So let me tell you what the proof of this a little bit. So the sketch of the proof. So always the first step is to quotient by G, so or by A. You have an A action on a finite variety X, and then you take the quotient. Now you find a bounded n complement here, which we know that exists by Virchow. And then you put it back, and what you obtain here, that I will call X comma V, is a A invariant n complement. So then the question is the following: you have a finite variety and an A invariant n complement. N is fixed. It only depends on the dimension, because when you quotient, the coefficients that you obtain are standard. So the set of complements doesn't depend on the coefficient set. Okay, so you ask yourself the following question: what if A goes to infinite? If A goes to infinite and n is fixed, what can you say about the pair? So with A going to infinite, I just mean that you take a sequence Zm to the k, where k, well, you were saying that k was 2, and m is going to infinite. So let's look at the more naive example that we can think about. Let's think about P1. So you have P1 and you have 0 and infinite. So if you have an automorphism group, A acting on P1, there is a billion, and it has order 4, it could do funny things, right? It will have 2 generators and move things like this. But as long as it has order greater than 4, you know that the only possible action will be fixing your 0 and your infinity, and then you just rotate with respect to the, rotate with respect to the multiplication of some root of unity. Okay? So this tells you that on P1, A invariant 1 over the absolute value of A complement. Oh, sorry, no, I think I should write. Can only be 0 plus infinity. So what I'm saying is that once you fix n, well, let me just write n here for some n fixed. So once you fix n and increase A, the action, the outcome that you will hope for is that you make your boundary to become reduced. So it's only 0 plus infinity. And then there is this theorem this theorem, well, that it was worked with by a lot of people, Chelsea, Procoro, Brown, McKernan, Sbaldi, blah, blah. But it was actually finished by these people, I think, in 18, is that if you have a log canonical pair such that Kx plus B is 0, is Q linearly equivalent to 0. Well, actually, I think they have better conditions than this, but we will apply this version. Such that the dimension of X plus the row of X minus the sum of the, so this is the sum of the boundaries, the coefficients on the boundary, is 0 implies that X comma P is storic. Okay, so the idea of the paper is really simple. Then the computations, well, one has to play a little bit, but it's not so hard. So you take the quotient and then you leave an A invariant and complement. Okay, so the aim is to apply this, but maybe we cannot apply it in the starting pair. Actually, this same example shows this because the row of this is a large row. So actually, the row of this example is moving with n. It's like 2n plus 2 or something. So we try to do the obvious thing. So you start with your bounded, so a sketch, a really sketchy sketch. So you start with your A invariant n complement of the surface. And then you go to a terminalization of X. So we call this Y comma By. So here Ky is terminal. And By is just the log pullback of XB. So everything is still A invariant. And then you run a MMP, which will either terminate with ZBC, which is bounded, or it breaks to a modifiable space that actually one can check that goes to B1 with the reduced boundary 0 infinity. So now the game becomes pretty easy, right? Because if it is bounded, it's not hard to prove that actually it has a transaction. If you have a bounded family and a large abelian group acting on your varieties, you can actually prove that there is a transaction equal to the rank. The dimension of the torus is equal to the rank of the large abelian action group that you have. Okay, but what happens in the fibration case? In the fibration case, what can go wrong? So now we know that the row A of Z is 2. So then one can try to apply a version, an equivariant version of this paper. It's not hard to prove that it also works equivariantly. But here there are some complications, right? Because right now, then you will have a splitting of A acting on the general fiber and acting on the base. So the action on the base will tell you that the outcome will be something like P1 with 2 reduced points. And the action on the general fiber will tell you that the general fiber will look like P1 with 2 reduced points. So somehow we're in good shape because after recompactifying, we can show that the picture should look like this. So you have some fibers with coefficients 1 all over around. And then in the general fiber, you have 2 coefficients 1. But there is a main problem, right? So if we want to get our countings right, we need 2 horizontal divisors over the base. But it may happen that this is just some divisor that ramifies. So let me do it like this. It's some divisor that maps 2 to 1 to the base of the modifiable space, but it ramifies. And actually, one can prove that it must ramify along the stuff that already appears with coefficient 1 on the vertical side. So here the main point is to prove a lemma that says the following. If AF is large enough, then no divisor with coefficient 1. So there is a comment on the chat. Nice work, interesting. Okay. No divisor with coefficient 1 ramifies over the base. So this actually reduces to do some toroidal. Oh, you have to leave. Well, nice to meet you. Have a nice day. This reduces to some toroidal computation. But then we will have 2 sections with coefficient 1. And then the last part of the paper is just trying to write down an A equivariant version. Well, it's not the last part, it's sort of the beginning of the paper. Write an A equivariant version of this theorem and apply it in this picture once we prove that there is no ramification. And that essentially concludes the book. So let me finish by posting some conjectures that I've been working on. So the conjecture is the following. So there exists a constant Mn only depending on n, satisfying the following. Let X be a phenotype variety of dimension n with A is equal to Z m to the k inside out of X with m larger or equal than Mn, then X contains an open set U isomorphic to Z times Gm to the k, which is A invariant, and A acts trivially on Z and by roots of unity on GMK. Well, I mean, this is the main conjecture. Then we can also say something about complements on X. So the conjecture is essentially that if you want to understand complements of X, essentially they come from complements on Z, on some compactification on Z. But well, writing down that part is a bit more technical. So let me think here. So this is the main conjecture I'm working on nowadays. But you see, this conjecture is about phenotype varieties. So there is a question that for me is entirely open. So question, if a Klt singularity contains a large abelian group, you can even say that has the same rank as the rank of the abelian group is equal to the dimension. How the geometry or how the existence of A, well, when I say that the Klt singularity contains a large, I either mean inside the pi 1 or that is an action, which is essentially the same. How the existence of A reflects on the singularity. So I've been thinking about this question for a long time, but I have no single clue how to tackle it. I have some numerical conjectures, but those are a bit technical. So essentially, it's something about existence of some nice complements, but I don't have any geometric conjecture. I would like actually to say something about the geometry. For instance, I mean, a priori, one would think that A becomes toroidal, but there are many examples that show that this is not necessarily the case. So there must be something weaker than toroidal, but close enough that should be a reasonable conjecture. But for so far, I can only conjecture the projective case, and I'm currently working on proving this statement. So this is all I have to say for now. Okay. Is anyone still alive?
Yeah, we're all alive, and the conjecture is very interesting, of course, and like so many things coming together. Okay, let's thank Joaquin. Okay, any well, so my comment is that I especially like the last conjecture. It looks
I actually feel
optimistic in a good sense. That some structure is simple. Okay, any questions?
maybe I have a comment, maybe very general. I think most of the questions can be addressed to Calabi-Yau side of geometry. You see, if you replace Fana with Calabi-Yau, Klt with log canonical, right?
Right.
But then maybe you should replace Jordan or abelian with nilpotent.
Okay.
I expect that this should work. At least in two-dimensional case, it works perfectly, right? Do you agree?
I think the two-dimensional case would be easy, but the main problem with that direction, I think, is at some point you hit this wall of working with the topological boundedness of Calabi-Yaus, right? Of pure Calabi-Yaus.
Yes, yes, but actually here you can consider two things. First, rational singularities. Rational log canonical means that, and in this case, your exceptional divisors will be rationally connected. So
right.
Pure FT varieties in some sense, right?
I see your point. So your point is that maybe if one works with rational log canonicals, the same work can be applied to sort of avoid going into the Calabi-Yau world. But I understand these conjectures should be more general. And then in the case of Calabi-Yaus, you expect some sort of elliptic action instead of torus actions. Although I think that the problem of not having topologically boundedness of Calabi-Yaus seems to be a really hard wall to try to prove things in that direction in dimension 3 and higher.
It were some works of Ishii and Fujin about indices of,
right.
purely, of strictly log canonical singularities. So they are bounded. And they use some kind of, you see, some kind of these arguments with blow-ups and covariance, so like this.
No, but what I meant with boundedness of Calabi-Yau is that, I mean, I think if you try to prove these cases in higher dimensions, the log canonical case, at some point you will need to use the fact that all Calabi-Yaus have finally many possible topological types or something like this. Maybe in dimension 3 one can go around this, but in higher dimensions I think it would be I have thought about the log canonical case as well, but I always fall into the same problem. Like, how do you control the pi1 of a pure Calabi-Yau variety? And this seems to be pretty hard.
Of course.
Yeah, but I think that maybe what you mentioned is really interesting for me. Maybe the rational log canonical case is something that is doable.
Okay. Okay.
Okay. Any other questions? So if no, okay, Joaquin, thanks again for.
Well, thank you for the invitation.